Hello. All right, perfect, awesome. Good morning, you all. I think this is the first session for the day, so that's good. Um, Quick introduction. I'm Santosh Kumar. I'm from Agnostic. I lead the research and product team at Agnostic over there. And the product that we build is called Covalent. And today we are kind of going to give you a flavor of how you can build real life, full-fledged production-ready applications directly from Python on your side. And with me, I have Ara, who's a research software engineer within the team. And I'll give a quick introduction on what we do, and then kind of let you guys know why we do what we do, and then I'll pass it to Ara to give an example of where, hopefully, today we'll build a POC startup idea from our end, and I'll explain the startup idea as well within an hour that we have over here. Before doing that, quick question over here. So how many of you here have played with LLMs on your side? Like, oh, that's great. Wow, that's a lot of people. And how many of you here have deployed LLMs at scale? Hi, great. Hi, that's nice. And rather than deployment, trained it in at scale. Anyone? Fine-tuned? That's good. Hey, so this is going to be interesting for everyone over here. At the end of the talk, you'll kind of learn how to fine-tune from scratch, deploy models, not just at POC, but at scale for an end user to serve thousands of users on your side. And cool. Okay, so let me start with why this is actually hard and what we do at Agnostic from our side. So most of the team from our side come from high-performance computing background. So I'll give you a flavor of what high-performance computing is and what general compute is and why it's typically hard to kind of productionize LLMs, mostly because of the fact of how complicated infrastructure is for GPUs and other high compute stuff. So anyone here from academic background, from scientific computing? Oh, okay, I see one raised hand, 2, 3, 4. That's great. So those people kind of know what high performance computing is. But in general, high performance computing is like a large scale compute that you typically handle for things like scientific simulations, complex financial calculations, modeling really large earthquake systems and all those sort of things, and where you use thousands and millions of cores to simulate something on your side. And it can even use accelerated computing like GPUs, quantum computers, or any of these kind of systems in. And typically to run things on these kind of systems, you have a separate software architecture that you run it in. And one of the most famous stack that you have is something called Slurm. And if people here have fine-tuned or trained model, you would have used Slurm on your side. And the goal for there is that you have a huge pool of compute resource. Typically, it's like national labs, large data centers, and all those kind of places in. And you have an infrastructure layer, which is called scheduler. And thousands of users just come in and submit their jobs in. And usually jobs wait in a queue. There is no concept of auto-scaling because it's a one-off packed job that you send in that runs for a couple of hours, couple of days, and even years together. For instance, OpenAI training can run for months together on its side in a GPU if you're running it in. And kind of this usually doesn't work in the cloud. These high-performance computing centers or on-prem systems, you SSH into a machine, you go to a VPN, you kind of submit your job over there, get your result back, and all those kind of things in. And to build applications on top of such high-performance computing stack is extremely hard. It's usually meant for research, one-off calculations that you're doing over there. On the other side of the setup, where you have the general compute, and I'm pretty sure everyone over here are familiar with general compute on its, and I assume the equal split of high performance and general compute audience over here. So, but general compute, as you all know, this is the compute that you have access to on the cloud. So you can think of your Lambda functions, EC2 instances, Google VMs, all those kind of system in. And there is almost, you have the illusion of infinite compute when it comes to general compute, which means you just ask for a resource and you get it immediately. And everyone over here who has kind of played around with LLMs know that you can't just access GPUs on your hand. And high performance computing by the very nature is very restrictive on its end, meaning that there is not a lot of access to it. It's a limited pool of resource that's being shared by thousands and millions of people in. And the general compute, there is a separate stack that you handle in, and typically the stack you use is something like Kubernetes or Nomad or all those sort of traditional software systems that you use. And now the goal there is to kind of, you have the same calculation or the same thing that you want to run, but you want to scale it up to thousands of applications or auto scale it and do all the sort of cool things in. And when we saw very few hands raised for productionizing LLMs on your side, The main challenge is when you're productionizing things, how do you combine these two things when it comes to stack? How do you use high performance computing and yet have a scalable applications built on top of it? And our goal at Agnostic, where we build up actually an open source product called Covalent, is to kind of create an infrastructure platform for people to run applications on high performance computing at scale on their side. We go beyond general compute. So for instance, you can attach quantum computers, ASICs, FPGAs, Raspberry Pi, doesn't matter. We give you a platform for you to write any kind of applications, be it training to fine-tuning, to deploying models, to running simulations, to simulating in quantum computers, to anything that you want to do. With that, I'll pass the mic to Ara, who will give an overview of the startup that we are going to develop over here. And there are more such startup kind of things that you can develop pretty much in a single notebook in our tutorials that you can go over, and this is one such example that he's going to show. Ara?
Thank you, Santosh. Hi, everybody. Right, so I have a little diagram, I guess, over here on the right. It's a pretty simple idea, but what I'm showing here is kind of the high-level overview of what I want this to do. So imagine a company where they have a service with which you interact by passing a simple prompt, and that passes through an interface, goes into a model foundry that's just going to be a gray box for now, and then what comes out of the end is a deployed LLM that matches the task that you've given it up here. So if you try to do this with in a more traditional approach, there's a lot of moving parts to put together. And you can see how busy this graph looks. I didn't go out of my way to make it look busy. It's just, I guess it's even a minimal setup here, and it looks quite complicated. So you'll have to manually set up your sort of access management. You're setting up storage in the cloud, as well as 2 different clusters for both doing the training side and the inference side. You have some repository for images. You have to manage GPU resources on your own, store your models, never mind connecting it all together in the end. And what comes out of the very bottom here is user-facing API endpoints. So this is removing all the high-level stuff from here, going a little bit deeper. You might have something that looks like this. So before I move on to what we're proposing that should look like, or a simpler version of it rather, just a quick note on perspective. So we've seen infrastructure kind of change quite a bit, or the approach to it change. Before, stuff like Kubernetes, where users are connecting directly to VMs, and the more modern approach has kind of revolutionized this a little bit. So it's a little bit more scalable, it's a little bit more robust. And in our opinion, something in AI that corresponds to this needs to happen as well, just to make it more accessible and more usable for everybody. So again, we're proposing Covalent as one approach for doing this. And what we hope to accomplish with it is to combine the robustness of HPC with the agility of modern container orchestration for AI development. Let me introduce real quick what you're working with in Covalent. So it's totally Pythonic, although you can run non-Python code with it as well. But you don't really need to. And what I'm going to talk about today are 3 basic components, and those are what you see here. So we have our lattices, we have our electrons, and we have services. So thank you. Yeah, I was a little bit stuck. I didn't want to push it. Okay, sorry about that. So 3 things to think about. We have electrons, lattices, and services. The electron and lattice bit come from our origins in science and scientific computing. But you can think of electrons as being tasks, so something like fine-tuning a model, something that runs once and doesn't really stay up. A lattice is what combines your electrons and your services. So that's going to be our main workflow. It's kind of like a main function. That's where we're going to collect everything and compose all the little pieces. And services are, well, they're services. So You can define something with an initialization step and then add your own custom endpoints to do whatever. So for example, you can have an LLM service. And here you would be loading the model, for example, and then down here just posting to the generate endpoint to generate a response. And I just want to emphasize the difference between electrons and services. An electron will be like a function that you can ship to whatever backend you want on the cloud. And a service is a service that you can ship to whatever backend you want on the cloud. Once I get into the code, we'll see how we decide exactly where these tasks or services run. But yeah, just to highlight a small difference. So the electron you might use for fine-tuning your model, but the service is what you'll use for doing inference with your model so that you can do it in real time. Okay, so here's what I'm going to show you today. This is the covalent version of the really complicated graph we saw earlier. So the startup idea, right? We'll have the user pick a model and just say, you know, I want to fine-tune this LLM to detect spoilers in movie reviews, for example. So that'll talk to a main agent, which is going to be a lightweight service running on just a couple of CPUs. And what that's going to do is orchestrate two other components, one of which will be a data generator LLM, so something quite large, maybe 8 billion parameters or more. And the other one will be a lattice that's going to do a fine-tuning and deployment workflow. What's going to come out of this is exactly what the user asked for. So a new model with an interface that's up in the cloud that you can interact with. You can have API keys for it, et cetera. It's a full-fledged service. All right, so I'm going to move on to the notebook now. I realize it might be difficult to read on your phone, but if you'd like to go to it on your laptop to follow along, I have the link up there. Just give everybody a second.
While you're taking the photo, like at any point, feel free to ask in questions, make this conversational. That's totally fine, and it doesn't need to be a one-way talk. And yeah.
Thank you. Everybody okay? Sorry about that bouncing icon. Just a little while longer. Okay. So if you go to that repo, you'll be greeted with this README that I also have here. Here's just the same thing we're going to do. And what you want to do is find the notebook called Zero Data Model Foundry. To follow along, just open it. If you want to run it later, you're going to need a Covalent Cloud account. You can talk to us about that. And there's just a couple extra steps to basically just set your API key in the environment file. Okay?
Yeah, just a brief for there as well. So you can do everything over here in open source as well. And where the Covalent Cloud part or the managed part comes in is we have a huge pool of GPU resource from our side, and that we can tap on demand, H100s, A100s, anything that you want. And so we'll be doing the live demo using the cloud account that we have in, so that we have immediate access to the GPUs, but you can pretty much do it with the open source if you have your own compute on your side. Thanks.
All right, let's look at some Python code, okay?
Oh, yeah. So this one, is it there still the talk? Okay. So this one, we are going to run this, the main agent that's going to run, and it's going to be a CPU bound one, so that's no GPU at all. This one, it's going to run, I think, Llama 838B. Yeah, so Llama 38B on its an 8 billion parameter. Yeah, sorry?
Quantized version.
The quantized version. So yeah, you can do away with a pretty small Llama as well, as long as it generates good data on its end. And then we are actually going to fine-tune Tiny Llama, I think, Tiny Llama, which is pretty small as well. So you don't need, you can pretty much do it in a consumer-grade GPU, this particular example as well on its side. Where this becomes a problem is if you want to scale this and have the end user serve, I don't know, thousands of people or whatever, that's when I guess you start hitting the hiccup on your end. Yeah.
Oh, right, sorry. All right, okay, let's walk through it. Step one is a bunch of imports. Bigger? that better? Unfortunately, this top thing also zooms in. But
go to Zen mode as well.
yeah, sure. Good idea.
Does this work? Does this look better?
I'm not sure. It's narrower. Can we go back? Let's see. Just get a comparison here. Does anyone think that's better? Yeah? Worse? Same? No? Okay. Just a sec.
And with the number of shortcuts in VS Code.
Yeah, this is more Zen, actually. All right. Cool. Yeah, nothing really to point out here. Just grabbing a couple things to use. So in Covalent, even though we're shipping stuff to the cloud, you can pretty much just work with the global scope normally. So there's not really anything special to do. You just grab your Python packages as normal. Two things to highlight here. I'm using the open source core for Covalent as well as Covalent Cloud. We'll see how those fit together. I have my enum for my GPU types, and then just some stuff from Hugging Face. So data sets, this is for fine tuning. Specifically, it's for low rank adapter fine tuning, which is much faster, as we'll see. So it's on the order of 15 minutes here. And then just a bunch of standard stuff. Covalent Cloud users, first thing you want to do, save your API key. Only do that once. I've set this up in my environment file. So yeah. Okay, here's one cool feature. And I'll get through this intro bit real quick. I'm just going to create also a volume in the cloud. I can use this thing as if it were a path in Python in my code. And that's just going to let me store my fine-tuned model somewhere for the service to pick up and load. Did you want to say something?
I was just going to say to grab in the API key, you just pretty much. Okay, so this is the application in the Covalent Cloud, and once you sign up and you get in, you get your API key that you can pretty much just copy right out of the box over here and paste it in, and that should give you all the stuff. And every other calculation and every other service that you host in will pretty much be hosted in your Covalent account as well for your end. But yeah.
All right. Cool. So we have storage. One more thing. We want runtime environments. So I'm going to create two here. This is the fine-tuning one. It's a lot more stuff here than the next one, which is just for, I'm just going to use one cool Python package just called VLM. Has anyone heard of VLLM? It's super convenient. Really nice to use. Not a very popular package, but I'll make use of it here just because it's so simple.
Yeah. And one thing to add here is, so what we are doing here is pretty much if you are developing an application using Kubernetes or whatever, deploying an application, you typically create a Docker image, I don't know, host it in and do a bunch of things, right? So what we are doing here is writing this will go back and into your Covalent account and create a Docker image for you on your site. So we don't deal with anything related to Docker or any infra that you need to handle in. And what this will do is you can actually bring your own compute inside Covalent as well. This will create a distributed Docker container that is available across clouds, across regions, and all the places, even on-prem systems on your side and in the background. And the volume that he just mentioned here will create a distributed volume that spans across clouds, across regions, and across other places as well. So what this means is you can pretty much fine-tune on GCP, deploy it on AWS, fine-tune on Azure, run your calculations on-prem, and all your environment, all your volume, storage, and everything will be accessible throughout the stuff that you are using it in.
Yeah, and of course the environments are reusable. So I don't need to go through this creation step every time. I'm just going to refer to it by name beyond this. So you can see the last time I ran the cell, it just told me it already exists. Okay, so let's get started with the actual components of this service thing I talked about, or startup rather. I'm just going to zoom out momentarily so we can see this. The first thing I'm going to show you is putting together the data generator LLM. Just going to get rid of that. Okay. So this is the thing that's going to take our prompt and churn out a bunch of synthetic data that we're going to use in here to fine-tune and deploy a smaller model. All right. Here's another important thing. Okay. I kind of alluded to this earlier, and let me zoom back in here for everybody. This is what we call an executor in Covalent. In this case, it's a cloud executor for Covalent Cloud. This is going to be where you codify all the compute resources and memory, and as well as a time limit if you want. In this case, you can see what I'm doing here. I'm using a modest 6 CPUs. I have 1 GPU, and I want that 1 GPU to be an H100. And I'm going to say, give me at least 48 gigabytes of memory, please, and leave this up for 7 hours. Now, this thing is totally modular, so I can take this and assign it to whatever electron/task or service that I'm interested in running with these particular specs. You can see also the environment is included in here. So when I come down to my first service, indeed I'm passing here an executor, the executor from up here, okay? Right, so the data generation service. This big string at the top, I'm sure this looks familiar to everybody. So the underlying model is Llama-based, and this is your typical type of prompt for Llama. And here's what I'm asking the LLM to do. So I'm telling it, you're a knowledgeable assistant who generates fine-tuning data for an LLM. Please generate this many data items for fine-tuning, for the fine-tuning task specified by the user. I'm yelling at the LLM to respond only in JSON, and it does seem to do that most of the time, which is nice. And then, yeah, just a couple more tags just to initiate, I'm done prompting you. Now here's some input from the user, and you're the assistant, please go ahead. That's pretty much what the last few lines here do. So let's look at how we define the service. You'll note that most of what you'll see here is very ordinary Python code minus just these decorators that come from Covalent. So the first step here is just an initializer. I'm not really doing much here. I'm just loading the LLM into memory. Once that's loaded, I can just infer real time. So I'll talk to it with my generate data endpoint down here. That'll take a task, optionally a return format. We'll see what that's used for, and a couple other parameters. We can look at this real quick as well. Just going to format the task into that prompt up there. So that task will go into here. What I'm also doing is making this part JSON just to impress upon the LLM that I want a JSONized output. Now, there are other packages you could use for this. Some really clever stuff that'll try its best to enforce parsable JSON like 90% of the time. I've forgone that here just for the sake of brevity. So we have quite a bit to get through here. All right, so let's look at the generation endpoint. I want this to generate data, so I'm going to batch my inputs. I'm going to initialize some sampling params, and basically right here, tell the LLM to generate that many data points. I'm going to make sure they're parsable. This will throw away a small percentage of what comes out, and then it's just going to return it back. And that's really it. That's the data generator service. So there's nothing, if you were to do this locally, assuming you have GPUs so you can run this, it would look the same. It would just lack this and this. So that's part of what's really elegant about Covalent. At least for the developer, it's just a couple decorators on top of very ordinary code.
Yeah. So quick briefer on what this decorator does. So what this decorator does is that it lets you host any function, we call it function serve, any function, high compute function you have with any backend as a final API endpoint that you can hit via REST or curl command on your side end. So once you have this function written out or this decorated function written down, and then just do cc.deploy of this function. What this will do is this will spin up a separate cluster, compute cluster for you in the background, which will have a CPU machine that runs as a head node and a machine that you have given us executor here, which I think is an H100 machine. For each of the new requests that comes in, it'll auto-scale that H100, run that query, get it back, and you can pass on all kind of auto-scaling requests and all those sort of things in. And you can even make it such that you just pass on to say, hey, I want the authentication to be true. You can even make it such that the endpoint is authenticated by API tokens, which you can actually see. I actually realize dark mode is pretty hard to look at. Let me just look at it here. Yeah, here it is. He has few of the models running in. You can create a new API tokens here as well, and you can curl this endpoint. You can from any place, and as and when the request keeps coming in, it'll auto scale to accommodate those requests as well. So the crux of this is we have created a scalable API endpoint, which uses high compute in the background for you on demand, serverless, with pretty much, I don't know, 3 to 4 lines of decorators ordered on top. Yes? Oh. Yeah. Is there a way to dim the lights, I assume? Oh, no. Oh. Ah, okay. I guess we can start the party in. Okay. Maybe this helps. Yeah. Yeah. So here you see that you have you can pretty much curl with it, get a token, run it in, and do all the stuff in. So in theory, if you don't want to host an entire service, you can just run a Llama here and use it as your private Llama chatbot to do whatever you want. That has a scalable A100, H100, or L40 or anything in the backend for it to run it in. But the main fact is now we will use this as a sub-service among 100 or 2 or 3 different services that we use to orchestrate a very complicated workflow that Ara is going to show it in.
So I guess just to summarize that, basically what Santosh is saying is that this piece here, you don't have to run it as part of this entire thing. You can deploy it in one line and talk to it the same way that this thing will talk to it once we have the entire thing up. Right, so that's one component. So here's, I'm also defining the service that'll run the fine-tuned model. This is the thing at the very bottom, and this is the interface you're gonna have with it once you have it up. So let's see what that looks like. Again, an executor, right? What I've done here is swap the H100 for an L40. I'm using a small model in this case. This is gonna be more than enough. And yeah, just same idea. We have an environment specification, and we have memory, time limit, etc. So again, the same sort of interface here. I have a service decorator, and I have an endpoint decorator that comes from the thing that I decorate with the service decorator, right? In this case, there's a little bit more initialization to do. So I'm gonna grab the data files here. I'm gonna load the model, load the tokenizer, set a couple of properties on the tokenizer so I don't get annoying warning messages, turn it into a pipeline, and then return everything that I want to be used over here. So this is going to be literally everything, and it's when you write your endpoints, you don't have to accept all of that. So I'm just picking out the pipeline in this case. Yeah, and thanks to Hugging Face, this is actually incredibly simple. It's really just one line. Take the prompt, generate text. I'm going to grab the generated text and return it. I also have a stream endpoint. This is a cool thing we haven't seen yet. So you can have streaming endpoints as well in these things. And what that means is that you'll basically get the response back sort of bit by bit. And since this is a streaming function, what I'm doing here is basically I've decorated, the name is coincidental, but a generator in Python. So I'm yielding instead of returning, and I can yield whatever I want just to show little progress updates in my output. Streaming from an LLM is a little bit more complicated, as I'm sure many of you here know. So the code is correspondingly a little bit more complicated, but really we just go token by token, and we feed in everything that's been in there so far, grab the next one, and do a little bit of a special treatment just to make sure we have spaces coming out right. And then this runs in a loop until we hit either an end token or we just overrun this limit. And that's about it. That is the interface we're going to have with the models that are deployed by this thing. Here's the main agent. This is the user bit. This is the bit the user will talk to, as indicated by this very convenient arrow over here. Okay. Not a whole lot here. I'm just going to inform it via an initializer argument of what the workflow looks like that does the fine tuning. I've yet to show you that. That comes, I think, right under this cell. And then what this is going to be is a handle for talking to the data generator. We'll see what those objects look like as well, but it's pretty much just a Python client for the data generator service. So here's the main endpoint. This is what the user talks to directly, it's called submit. These two arguments are going to be passed in automatically from up here. And then it'll take the user's task and a data format optionally. The reason I'm doing it this way is this serves kind of the purpose of being a sort of a special tag that the LLM can detect to understand that, if I give it a sentence that ends here, the completion it needs to do is to provide a label. Now, you don't have to use this exact format, and indeed I don't in all the examples, but that's just one way of doing it here. And this is the model that I'll be fine-tuning in all the cases here. It's called Tiny Llama. It's a tiny implementation of Llama, tiny meaning only 1.1 billion parameters, as opposed to 8, 14, or 70. So when you submit, you're going to get a bunch of feedback coming in step by step. It'll inform you that it started generating. It'll generate and give us a little dot back for every little iteration of that. Then it'll summarize by telling us how many data points we generated, which will be more than the minimum. It'll save it, and what it'll do down here is just dispatch it'll dispatch the fine-tuning lattice. So once the data is ready, if I go back to this picture, so once the data is ready from this guy, the agent will automatically dispatch a workflow, and inside that workflow will be a step that deploys this. And really, that's what we're seeing down here. I'm also having it just query the result in a loop and give us a little dot so we can be sure that everything is running. At the very end, we'll just get an ID. It'll be a string of numbers, and we can load a client based on that. And that's all we're going to need. OK, one more thing. Here's the workflow that does the fine-tuning. Okay, this is going to look like normal code for fine-tuning something using a parameter-efficient low-rank adapter method. If anyone is unfamiliar with that, what that means is you can fine-tune the model not by fine-tuning all the 1.1 billion weights, but rather by adding a few extra layers, which have far fewer parameters and are much quicker to fine-tune. Pretty popular technique nowadays, and I got decent results out of this with, I think, about 15 minutes of fine-tuning as opposed to multiple hours. What I have in this data class is a bunch of parameters for fine-tuning. I'm not going to go through all that. This is just helping me make my function signatures a bit more clean. So I'll skip all that, and let's get into the fine-tuning task. Again, I have a task. I have an electron. I can specify where I want to run it with what resources. I'll do it on H100, which is a really good GPU, so I'm trying to do this quickly. And I'll set a time limit of 7 hours, but it's not going to come close to that. It'll be less than 30 minutes. And here's the task, right? So it's a task in my workflow. So I add the electron decorator on top, and I just say, here's your resources. Here's your executor. This, again, is very not unusual code. I have a quantization configuration, loading the model here, setting some configuration, loading the tokenizer, same thing, grabbing the data set, initializing a trainer. This is super convenient. And then this step will just kick it off. So this will take a while. And once that's done, we're just going to save it to a volume. And you can see this is my volume from the top. I'm just saying, it's up in the cloud. I can treat it like a path. I'm going to stick a UUID on the end of it just to make it unique. And that's it. Yeah, just going to save it. I'm going to return the path to it. This path will be consumed by this guy. So this guy will have access to the same volume that was used here and here, just because it's fully distributed. So with that unique file name, it'll be able to grab that model and pretty much load it and set it up for inference. Great. OK. And then, here's the sum total of the fine-tuning workflow. Step 1, do the fine-tuning. Step 2, run the service. Step 3, return basically a client to the service. Right, and then now to set up my quote-unquote startup, I have a lattice with 2 steps. Initialize the generator, pass the handle to the generator, to the agent, and inform it of the workflow that it's going to run. Right, so that is going to create this, this, and it's going to inform this of this. Go back there. Right. So in Covalent, if you want to run things in the cloud, what you do is you dispatch them, and that's exactly what I've done here. I'm dispatching that setup workflow, this guy up here, specifying the volume I want it to have access to, which was the volume from like the very top of the notebook, and I'm saying this is the workflow I want you to run for fine-tuning. So once you run that, it takes about, I don't have my time anymore. This was around 15 minutes. I have dispatch ID, and what more importantly, I have this. This is an ID for my main agent. Now, as long as that service is up in my account, which I believe it currently is, where's my browser? Function serve, just give it a sec. Yeah, this guy, I believe that's the same ID. So I'll be able to just load it and use it just like that. So when I run this, I get my client. You can print it, comes out with a bunch of useful information here. You can interact with this generically, by the way. So if you want to post requests to this from any other application, you want to do a manual request in your command line, go for it. Just add the endpoint and provide it with a suitable input, and it'll do its thing. So let's get into the examples, right? I did the one from the slides, so fine-tuning an LLM to detect whether or not a movie review contains a spoiler. I told it to do that and to use 3,000 examples of data. For this type of fine-tuning, that's actually pretty sufficient. And there's my progress printout. So I'll try to load the thing here, and I'll go through a couple small movie reviews. Hope I've done the imports right.
Yeah. While he's doing it in, so the main thing what we have done is we have pretty much, I don't know, in 40 minutes or whatever it is, we have deployed a full entire application that is going to do this complicated step. And the step is going to be a user comes in and asks in, hey, give me an LLM that can detect movie reviews inside of it. And what our entire agentic setup that's going to work on is an agent is going to pick up and ask an LLM to generate X amount of data to fine-tune a smaller model. And then there is a fine-tune step that's launched to fine-tune the smaller model. And then finally, the fine-tune model is deployed as well. And each of these components right now involves a very intricate set of compute requirements in it. So the main agent is a pretty trivial one that's running on CPUs. The data generating agent, it's a fairly large one that's running on H100s or A100s, I think. A100 GPUs. The fine-tuning step is a costly process that's running on state-of-the-art H100 GPUs. And finally, the deployment step of the model is running on since it's a cheaper model, L40s on its end. And this entire application, which we have now exposed as an endpoint, we have built it without Kubernetes, without Docker, Terraform, nothing on its end, purely on Python on its side. Now the final endpoint that you get in can be exposed just in a front end for you to serve as an end user to create an application on top of, which is like you can now have an AI Foundry model that anyone can ask in for it to generate any kind of smaller model, and then it will generate in. And of course, this is just a POC in the sense that Ara will probably talk about all the improvements that you can do to take it into from POC and MVP to a full-fledged product in itself, and how easy it is to kind of everything is modular for you to do it in over here as well. But go ahead, Ara.
Cool. So let's look at how it does with the setup. So for perspective, this guy is using a 8 billion parameter llama model that's been quantized. I think you're okay with about under 16 gigs of VRAM for that. And then the thing we'll deploy is Tiny Llama, which is pretty much the smallest llama you could probably get. Maybe there's a couple 100 megabyte one, but that's a 1.1 billion parameter. So that's about 1/8 the size of this guy. Right, so I've loaded my spoiler agent using my unique identifier. So I'm going to try to see if we can detect spoilers in movie reviews, okay? Here's the first one. So this ripping action adventure features stellar effects and a superb lead performance from Owen Teague as a timid simian who must rescue his clan from the clutches of a warlike tribe. So that's Planet of the Apes 2024. This was a very positive review. I don't think there's a spoiler in here. Let's see what the LLM thinks. So it'll complete that with, right? So remember I passed the hashtags over here. So no spoiler. I think that's agreeable. Here's another one from Metacritic. A lot of dull acting except Sir Ian McKellen and Andy Serkis. And you have an uneven movie with yawns aplenty. Yeah, that's a 0 out of 100 for Return of the King. So let's see what the LLM thinks about this one. So it says that's a spoiler. I disagree. I think that's actually not a spoiler. So maybe a nicer model or a little bit of tweaking here and there. We'll get to classify that more correctly. What I think is happening is just detecting the severely negative sentiment and assuming that reviews that include spoilers generally correlate with negative sentiments as well. But in any case, here's a couple that definitely do contain spoilers, and I'm sorry if you haven't seen these movies yet. They're very old. So Soylent Green is people. You're not supposed to know that until the end of the movie. Yeah, it's a spoiler, okay? And anyways, at the end you find out that it was Earth all along. Yeah, sorry about that. That's also a spoiler. Great. Thank you. Please hold the applause. So a second example, again, something bite-size. So this is going to be examples of bot responses that correct grammatical errors. So one thing to note immediately is it's pretty flexible in terms of how you prompt it, right? So previously I was saying specifically I want to fine-tune an LLM to detect yada yada yada. Here it's a bit more casual, where it's just give me examples of bot responses that correct grammatical errors. So those examples, I want them to look like this. I want to say there'll be an input sentence, and then the assistant will give me a corrected sentence. This is not actually formatted. This is just literally this string is passed to the data generator. And again, I have a unique ID for it. I'll load the client. Great. So here's a couple sentences. I'm just going to run 5 in one shot. I should have never got a pet. So that should be should have, right? Jerry and me argued about it. Jerry and I. He said, no cat bites its own tail, and that is the wrong it's. But if I had to choose, I'd rather get a dog than a cat, 2 errors, and all dogs bite their own tails. I know this is nonsense, but it's hard to, this was hard for me, okay? So let's see. Well, you can use Grammarly as well, okay? You can get a Grammarly subscription if you don't want to do this. Let's see how it does. I should have never got a pet. Jerry and I argued about it. He said, no cat bites its own tail. But if I had to choose, I would rather get a dog than a cat. All dogs bite their own tails, which is false, by the way. All right, last example. We're going to fine-tune an LLM to translate a sentence without any emojis into a string of only emojis with roughly the same meaning. So I don't know how many emojis exist, but that's not necessarily doable for every sentence, as you can imagine. In this case, I'm just going to use a pipe character to do the separation, and that's what my data will look like. So load the client. Dancing with my cat. Let's see what we get. Okay, cat, love, that's all right. Got a brand new car. Yes, car, money. That's okay. I think that maybe that could mean got an expensive car, but if it's new, it's probably not cheap, right? Paint me a scenic mountain, Mr. Ross. There we go. Bob Ross is not in the emojis, but we have the mountain. So let's eat. Fork, tongue, good one. Burning Man, the festival, not a man on fire. But we just get fire. Okay, close enough, right? All right, thank you. That's it for the live portion here. I'll just go on back to the slides for just a couple more remarks. Do you want to take the spit, Santosh?
Oh, yeah, for sure. Cool. Okay, so we just saw how we kind of pretty much created a MVP that you can pitch to investors as a startup idea to do it in, and know that it's a pretty complicated setup that you have had it in. So you have no training data, you had nothing on your hand, you just out of thin scratch use 2 models to create a new submodel that are cheaper to run on a scale on your end. Okay, let's see how you can kind of improve this product upon and what it actually takes to improve this product in. Okay, let's say you as a startup owner now decide that, hey, I'm going to have 2 sets of users, or actually tier my user application such that few of the users get their trained model pretty fast and few of them are going to get it slower. So I don't know, basic tier and an advanced tier. And what this would typically involve is spin up a separate Kubernetes cluster that has separate set of pool of queues and resources of A-hundreds, H-hundreds, and different kind of compute resource, and re-architect your entire architecture. But with this kind of setup in, what this would pretty much involve is, just swapping a single line of executor to say, hey, I'm going to have a list of resources like, a T4 to train on, or H100 to train on, or V100 to train it on. And then you can even let an agent decide which one it gets in based on the quality that the user asks in or the time that the user gives in, and then price them accordingly. And this with Covalent is just swapping a single line of decorator on top to say, swap your executor and everything else happens in the background for you. No need to rewrite your infrastructure code or redeploy your Kubernetes cluster or anything on your side end. And this entire application still fits within a single Jupyter notebook that you can build it in on your side. And in fact, I think we just put out this tutorial like a couple of days ago, which is like you can have multiple agents working together to kind of refine and choose the quality of the data set that it's creating in as well. Let's say you want to improve the quality of the data set. Then you can have things like, hey, check the clarity of the data set that you're getting in, check the precision of the data set, creativity, relevance, and all those kind of things in. And this will create a better model and probably a better final result for you to give your end client in. And to add this entire setup, I think there's a tutorial up in our blog right now that just does this. And this is probably 30 to 40 lines of Python code again that you can just add into your normal workflow and then kickstart it on your side. And oops, is that the last one? Oh, no, this seems the last one. Hey, cool. Yeah, so I guess with this, we kind of end in our talk in, where the goal is for us to create an entire application within 1 hour, but I think successfully we finished it within close to 45 minutes from our end. So any questions, we are here to take it in. Oh, yeah. Yeah. Yes, of course. And in fact, let me kind of, I'm not sure if he has this set up in. Let me log into mine. Could you hold this in? Q. Okay, so we go beyond machine learning as well, as I said. And so I'll quickly show you an example of, in fact, how to experiment with the platform or with high compute on your side. So my research team does, so here is an example of a complicated chemistry machine learning example where we try to simulate a bunch of molecular systems using machine learning models and actual high compute calculation on its end. And what this would involve is a pretty gnarly graph that you see over here, which has such complicated dependencies, and each has its own resource. So for instance, predicting the next configuration of a given molecule might involve, I don't know, let's see what it's happening in, 24 cores of CPU that it's running in without any GPUs on its side. And while this is running in, you get in live STD out, your actual code that you have written in, the inputs you pass, the results you are passing it in. So this is truly meant for you to interact with high compute in an iterative, real-time manner on your side. Sorry? Oh, yeah, you see that. I don't think I have any errors in this. Okay, but yeah, you see the errors coming out as well on your side end. And you can even share it with other folks while it's running in to say that, hey, here's my experiment that's running in. And you can share it with anyone else on your side who has access to Covalent Cloud on its side. And the most key important thing is, you see this pretty complicated graph that you have seen here, right? Which includes so many tons of GPUs and CPUs inside all of these things. Ooh, I don't know why it's including in. But ultimately, it ran for 2 hours, and the cost is just $3. And the reason for this is very critical because what we do is provide serverless high compute on its end. So what that means is your function only runs on the high compute when it needs to run on high compute, which is which is the norm that is typically in high performance computing scientific community. But people accessing GPU right now, people spin up Jupyter notebooks and GPU to code and run and other things. And I was actually at one of the conference at MIT a couple of weeks ago, and the recent paper shows that in the cloud, only roughly 30% of the reserved GPUs are being used for actual computations, and 70% just goes to development, random idle time, and other things, which you are paying for actually on your side. So running serverless high compute is the main goal for us building this entire platform. And so to cut it short, yes, we do allow for iterative experimentation that you run in on your side. Yeah. Yep. Oh, so you just pay for the serverless part that you run it in. So first of all, you can bring your own compute and you just pay for the orchestration piece, which is what we do from our side. And for the rest of it, it's on demand that you just run it in. So you can spin up thousands of H100s right now and pray for the millisecond that you use on your side. And yeah. Oh, yep. Oh, that's a good question. So, oops. Our initial goal was to kind of unify all the high compute platform, and our focus was on heterogeneous computing, which is turns out to be interacting with quantum computers and classical computers. And the problem we were trying to solve is to run anything useful in a quantum computer, it needs to talk to a classical computer millions of times a second on its end. And there is huge set of orchestration involved to run these algorithms in. So we build a framework which enables us to do it. And it turns out doing that also solves the problem of accessing high compute across in a distributed manner from our side. And that's how this product evolved on its end. Oh, yeah. Yeah, in fact, yeah, that's a good question. And that's what I thought I had as a next slide in which I didn't have in. So currently, oh, actually, we did have it in on its side, the multi-agent setup. And so the goal would be to indeed augment it via, where is the other way? Oh, okay. Yeah, so the goal would be to have in a bunch of agents that are working with the same powerful model as the backend brain for it to make sure that the data that you generated is indeed the quality that you want to have it in. So if you actually look at our blog right now, you can make and define agents which checks the clarity of the data set that you have generated, the precision of the data set that you have generated with respect to the original prompt that you gave in, the creativity. Maybe you want more diverse set of data that you want to handle it in. So you can add all of these in a loop, which we actually have in one of our blog posts or tutorials right now, actually, that's up. And that can enable you such that the data that you generated keeps on iterating until it satisfies a certain quality, and only then is used to kind of train it in on your side. And after that, you can have which is the one slide I was looking for, with the final deployed model, you can have guardrails over there to check and assess the quality to say, hey, how good it is doing on my test data. If it's not doing good, then re-kickstart this entire step again, which is going to take another 2 hours or 3 hours to do it in, and then deploy the final model. And of course, it's going to come at a compute cost for you at the end of the day, which you can pass it to your end users on your side. But yes, so these are kind of the iterative additions you can add to the entire process that you are making it in. If there is no question, actually, we are in booth 221. Yeah, 221 from our side. Yep. Yeah. Mhm. That's a good question. And so we have a basic guideline in, but what we will be coming out soon within like a month or so is a concept called recipes from our side. So what that will do is pretty much put this entire thing as a single line recipe with everything abstracted for you to do it in. And we are going to let in people build their own recipes as well. Our main preview is how to run workflows in high compute. And it turns out you can neatly package these kind of setup in an entire workflow with predefined compute on your side. And so it'll be as simple as, from Covalent AI recipe import, zero data generator, and then dot deploy or dot dispatch. And you'll have this entire thing deployed with their respective resources on its side. Yeah. Oh, yep. Yeah, that's a great question. So our current customers are indeed enterprise folks, and we have a good set of startups as well. The way that we work with them is Covalent at the core. What we have built in is not the GPUs that we have in, which is of course good for startups coming in, but this entire orchestration engine control plane that we have built in. So for enterprises coming in, what we let them do is bring your own compute. So you don't need to use our GPUs. You can attach your own on-prem GPU cluster, AWS, GCP, Azure, or anything to us, and we have a patented setup where we just interact with metadata to orchestrate it completely on your side. And having said that, the other part for the data plane, the volume storage that you just mentioned, that can be brought on your own as well. What that means is you can pretty much attach your own account for the data plane as well as the compute plane, and just let us do the orchestration from our side. And you just work with Python, and everything else happens in your own account on your side completely. And of course, you can cloud burst to our pool of GPUs as well if you want to. Oops. Okay, it's back. Awesome. Yep. Thank you, folks. 221. If you guys want to have a chat, see you all.